S. Chan presents educational video lectures. Difficult concepts made easy. Study anywhere, anytime.
Welcome to S. Chan Academy, and I am Anmol Bhatia. The topic that we are doing is conservation of angular momentum, and the course that we are studying is engineering mechanics. So, in our previous videos, we have discussed in detail that what is angular momentum and how this is applicable to the rigid body. Additionally, we have seen certain definitions and certain numericals. If you haven't watched those videos, you can visit the playlist of S. Chand Academy channel.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box.
Now we'll be doing this topic, which is conservation of angular momentum. In my previous videos, we have discussed that we have two categories of systems. One is isolated system and other is a non-isolated system. So we have discussed about this isolated systems, in which I have told you that this net torque here is zero. Net torque on the particular components, that is particularly zero. That means the derivative of this angular momentum is equal to zero. So dl by dt is equals to zero. So when I integrate it, I'll get a constant term, and that indicates that angular momentum equals to constant. That means initial angular momentum is equal to the final angular momentum that we have discussed in the previous videos. So what do you mean by this conservation of angular momentum? So is this particularly states that the overall or the total angular momentum remains conserved, or it is constant. This I indicates the initial state, F indicates the final state, and L is conserved separately for the three particular directions. We would be discussing the case of three dimensions here, and for the three particular conditions x and y, x, y and z, this angular momentum is conserved. So particularly we will be discussing about this isolated system, in which sum of all these angular momentum is equal to L1 plus L2 plus L3, and that value is equals to a constant. That angular momentum can also be represented as I omega. So I initial omega initial, that is equal to I final omega final, and as per the definition of the conservation, this also remains constant. Now let us have a look at an example that particularly indicates the conservation of momentum concept. So I'm reading that question. It is mentioned that a puck of mass m, that is having value 0.5 kg, and that is attached to the taut cord. So this is a taut cord, and that taut cord is passing through the small hole. So this is passing through the small hole in a frictionless horizontal surface. So this is a frictionless horizontal surface, and it is being passed through that small hole. The puck is initially orbiting with the speed of initial velocity of 2 meters per second. That means this particular puck is moving with the velocity of 2 meters per second in a circle with the radius mentioned to us. Now this cord is slowly pulled from below, and it decreases the radius of the circle from 2.1 meter. So earlier it was moving with the velocity of 2 meters per second, but it was having a radius of 0.2 meters. But when it is pulled from downward, the radius decreases. So the radius becomes 0.1 meter. So we are required to calculate that the puck speed for the smaller radius. That means we need to find out what is the value of V2 and the tension which is there on the cord for the smaller radius. So I hope you got the question. And the requirement is particularly the calculation of this velocity and the calculation of the tension which is there in the cord at the smaller radius. So how can you do that? You have to write initially all these values mentioned in symbolic presentation, like mass is mentioned, initial velocity, radius of the initial value, final radius is mentioned, and Vf, which is the final velocity that we need to find out. So firstly, we need to check whether this is an isolated system or it is a non-isolated system. So this particularly is an isolated system in which there is no net torque acting on the system. So that indicates that this angular momentum remains conserved. So initial angular momentum is equal to the final angular momentum. And angular momentum is r cross p. That means p here is mv. So that would be mv into r sine theta, because this cross product can be elaborated in terms of sine theta. Additionally, this was perpendicular on the surface and it was moving. So theta is 90. So we have substituted 90 so that this value of initial angular momentum comes into picture, and the final angular momentum also comes into picture. So when I equate both of them, I'll get this value, which is r initial over r final into vi. We can substitute this value and this Vf can be obtained. And lastly, this tension, if it is required, so mass into acceleration, which is that moving acceleration which is there in the system, that can be represented. So we'll substitute the values and we'll get this value of this torque, and that comes out to be 80 newtons. So this is particularly the case in which the angular momentum remains conserved and the system is a three-dimensional system for a particular rigid body. Now, another case of that isolated system. You might have seen Shaktiman serial. It was there in early 90s, and it was mentioned that when the character moves, so that particular character moves in a particular direction with both the arms open, and when that character takes a flight, so that arms are closed like this. So after moving in this particular manner, the arms are closed. So why that particular character closes that arms? So that particularly would be the case of this angular momentum that remains conserved. That is for an isolated system. Let's say this person is sitting on a bench and having certain weights on his hands, and that person is moving or rotating continuously with the help of this angular velocity, and it has certain angular momentum also. And then what happens when that person takes those weights towards this side? So this speed increases. So with the speed with which that person is rotating, that speed is increased. So the reason behind it is this isolated system in which there is no net torque about this particular z-axis, and angular momentum remains conserved value. So the moment of inertia, it particularly changes. That means it particularly gets a change in the angular velocity, and the reason is the similar case of and conservation of angular momentum. Another good example of this case is how do we control this spinning action in this particular condition in which a person is taking a jump, let's say from this location to this location, and that controls the spinning action. It moves in a particular spin. So this is also the case of an isolated system in which no net force is zero, in which the net force is zero and the angular momentum remains conserved. That means I omega also remains conserved. So initial value of this angular momentum is equal to the final value of this angular momentum. Right? So change I is curling up or stretching out, spin rate must be adjusted. So curling up or stretching out. So overall the value of this angular momentum remains conserved, and moment of inertia here, that particular part changes. So this is one of the another example that elaborates conservation of angular momentum. Now we have an example. So earlier example we have seen for checking out the case of angular momentum. Now this example again is an indication of a 3D part in which you can see a child, let's say that child is of 40 kg and that child is running at 4 meter per second, jumps tangentially on a stationary circular merry-go-round platform. So the child is coming in with a particular speed and that jumps in over a stationary merry-go-round platform whose radius is mentioned to us as 2 meters. And the radius is mentioned to us, whose moment of inertia is 20 kg meter square and there is no friction. What we need to find out, we need to find out the angular velocity of the platform after the child has jumped on it. So the child was coming running and he jumped on this platform, and again this merry-go-round started revolving. So we need to find out what is the angular velocity of the platform after the child has jumped on it. So we were discussing about the solution of that particular problem in which the child has stepped into the surface and then we have to find out what is the value of that. So in this, we have to follow this procedure in which the moment of inertia of the system is equal to the moment of inertia of the platform plus moment of inertia of the person. That means the merry-go-round would have some value of this moment of inertia, and we have the moment of inertia of the person. Assume the person to be treated as a particle. So we have two particles in which a person when moved towards the center of rotating platform, so moment of inertia decreases and the angular speed, the overall angular speed, that must increase since the angular momentum is having a constant value. So you can see that the person was standing on the surface and the platform is rotating about its axis. So this person would have a certain value of inertia on the surface. So we have these values like I is mentioned to us, Vt is mentioned to us, and the mass of that particular child is given to us, radius of the platform is mentioned, and initial angular momentum was 0. So we have the value of angular momentum total, that is equal to sigma I omega and I omega summation, which is for the initial and the final value. So for the initial value, I have told you that we need to consider the sum, which is the initial angular velocity plus additional term, which is mvr. So this omega part is 0. So mass of the child into the velocity, which is the tangential velocity multiplied by the radius. Additionally, the final one, which is I into omega. So for I, we have to use this formula, which is the sum of the two, which is the platform and the particle. So we have the initial value, we have the final value. So as per the conservation of angular momentum, we have to keep both of them aligned so that this omega final or the final velocity can be calculated out. So this is the final result. So we stop here for a short break. After coming back from the break, we will learn the concept of this angular momentum with the help of certain numerical problems.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back after the break, and I am Anmol Bhatia. So we are doing the concept of angular momentum's conservation, and now in this part of the video we will be learning the concept of rigid bodies and connecting that same concept with the rigid body concept. So the topic is related to the rigid body concept. Let us first understand that what is a rigid body. So if between the 2 points you have the distance does not change during the motion and under the applied force, the body is termed as a rigid body. That means you have two particular forces. You have applied a force on a particular component, and the distance does not change for that particular body. So that body is particularly termed as a rigid body under the application of a required force. Second is the case when we have to understand different types of motions. So we have a categorization of different types of motions. Firstly, we have the translational motion. Second, we have the rotational motion, and we have the combination of translational and the rotational motion. Now let us understand those particular concepts, like what is a translational motion, what is rotational, and what is the combination of all these translational and rotational. So as per the definition of the translational motion, if all the points of the body moves in a straight line, so you have a body in which the different points of the body are moving in a straight line, and those movement particularly is parallel to each other. Let's say you have one point on the body and it is having a motion, and then you have another point on the body that is again having a motion. The third point is again having a motion. So all these are having a motion, and those movements are in a same parallel line, same straight line, and those lines are parallel to each other. So here you can see that the velocity of those points is same. So the velocity here is indicated as the same as per the definition. Right? So this is called as the translational motion. Now the rotational motion. For the sake of this rotational motion, if I, let's say, consider the simplest type of rotation, in which rotation is about a fixed axis. That means I have a rod and I am rotating that rod about that fixed axis. So all the particles will move in circles of different radius. So if there is a particle, so it is moving, if a particle is there on the surface, so it will be moving on the moving in a circle, but that is a different radius part with a different velocity. So here it moves with the different velocity. This particle moves in a different velocity. This moves with a different velocity. So the center of the different circles is there on the axis of rotation. So if it is there on the axis of rotation, we name it as the rotational motion. And if there is a combination of both of them, we name it as a combinational type of category. So if both the motions are present in the body, then it is termed as the combination, and the name particularly is called as a rolling motion. So that means if the body is rolling about this point, and additionally it is moving like this, so it is having a rolling motion. So the outermost part of the body, which is in touch with the other surface, is at rest. So it is called as a rolling, or you can say the pure rolling motion. So in this we have learned the concept of translational motion, the rotational motion, as well as rolling motion. And the rolling motion can be a category in which it is a case of a pure rolling motion. Now we have to understand this rigid body concept with the help of certain principles. So first principle that would be used here is the work energy principle. This work energy principle we have already learned in our previous videos of kinetics and kinematics category. If you haven't watched that video related to work energy principle, so you can visit the playlist of S Chand Academy channel. So this work energy principle particularly indicates the relation between the two tensions which are there, and U is basically indicating the energy. So T1 plus this internal energy, that is equal to T2. Additionally, you have this kinetic energy of this rigid body. So for calculating this total value, you have a case of half mv square and half I omega square. So this half I omega square is one of the energy, and half mv square is another energy associated. So half mv square is associated with the mass center G of the body, and half I omega square is associated with the rotation of the body. So here in case of a rigid body, if it is moving, and if it is moving with the center, so as per the center of gravity, if it is moving, so it would be having the kinetic energy. And additionally, if it is rotating about this axis, it would have this energy, which is half I omega square. This part we will be using in the coming numerical. So this is, let's say, the object, and this object is having this center of gravity, which is, let's say, a point G, which is the center, and it has sum of all the forces acting, and that can be denoted by the formula, which is mass into acceleration. And when this body is rotating about its axis, so it may have this formula. This may have this total value of this energy, which is half mv square. Now let us understand this concept of the rigid body with the help of one numerical. So a 240 pounds block is suspended from an inextensible cable which is wrapped on a drum of 1.25 feet. So I have taken bigger units, not in this SI, but in order to denote the bigger unit, I have to choose these values like in feet or pounds, right? And it is mentioned that it is wrapped around a drum. So there is a cable which is wrapped around a drum, which is radius rigidly attached to the flywheel. So there is a drum which is attached to the flywheel, and the drum and the flywheel will have this combined centroidal moment of inertia as 10.5 pound-feet second square. At that instant which is being shown, the velocity of the block is 6 feet per second, that is mentioned, and that is directed downwards. This is directed downwards with that weight also mentioned here. Knowing that the bearing at A, and that there would be a position A, so the bearing at A is poorly lubricated, and the bearing is equivalent to the couple which is moving with a magnitude of 60 pound-feet. So this bearing is moving is with the couple value of 60 pound-feet. So we need to determine the velocity of the block after it has moved 4 feet downwards. So there is a distance mentioned to us that this block has moved 4 feet downwards. So the distance is mentioned to us, the velocity is mentioned to us, the weight is mentioned to us, and the couple is also mentioned to us. And additionally, this moment of inertia is also mentioned to us. Now we have to divide this with certain positions. So firstly, we have to look at the position number 1, in which there are two things. One is a drum and the flywheel, and another is wrapped with the cord. So we have to look for this T1, which is the initial kinetic energy, and that would be equal to half mv square plus half I omega square. So herein half remains half, and this mass, although this mass was given to us in pounds, so this weight is given to us in pounds, so W equals to mg. So from there, this mass can easily be calculated. So 240 pounds is mentioned, so we have to put in the value of acceleration due to gravity as 32.2 as per the different category of the units. Velocity is mentioned to us. I is there, which is 10.5 mentioned in the question. You can see the question. It is mentioned moment of inertia is 10.5, and this omega can be calculated by using this term r equals to v equals to r omega. So we can use that particular term v equals to r omega. From there omega can be calculated. So r is 6 by this v value, which is v equals to r omega. So v is 6, v equals to r omega. So v is 6 over this 1.25 feet is this radius. So from there omega can be obtained. So we can put in this value of omega. So on solving, this T1 is obtained, right? So this is for the initial part. Now for the second position, in which it was mentioned that the distance is 4 feet. So it moved with a particular velocity and it attains certain other velocity, which is v2. So herein we will calculate T2, which is the final value of this energy. That is equal to half mv square plus half I omega square. So mass is mentioned to us as 240 divided by 32.2 into v. We don't have the value of v, so we can substitute v2 here, and half I remains I, and this v2 can be calculated from the same formula, which is v equals to r omega. So v over that distance, which is r 1.25 square. So we'll get this value of T2 in terms of v2 value, because we need to find out what is the value of this final velocity. Then we have this principle that I have already told you. So T1 equals to U12 plus T2. But herein we have the value of this T1, we have the value of this T2, but we don't have this value, which is U12. So for that we have to use an expression which is W into S minus M into theta. So what is this W? W indicates this weight. Weight is 240 pounds. So we can substitute that directly. And S2 minus S1 is the difference between the initial and the final distance. So initial distance is 0 and the final value is 4. So we have the value that 4 feet. So we can substitute that S2 minus S1 is 4 feet. This one. And moment is given to us as 60. So you can put in the value of moment as 60. And additionally, if this theta is required, so you can see that it is having certain value of theta, and this distance that it covers is S. So we have this S equals to R into d theta. So S here is 4 feet and R is mentioned to us as 1.25, and d theta we already want to find out. So from there d theta can be easily calculated, and we can substitute that value of d theta here. So you'll get this value of 768 feet pounds. So now we have the value of this T1, we have the value of T2, and we have the value of U12. Substituting all these, we can find out the value of V2. And this is the final result that we want to find out. So this is particularly the case of that rigid body, which is connected with the help of certain weights. So this is the final answer, and we want to find out determine the velocity of the block after it has moved 4 feet downwards. So when it moves to 4 feet downward, we have to find out the value of this velocity. So we come to the end of this video, in which we have learned about the case of rigid bodies. We have learned about certain definitions related to the rigid bodies, and also we have solved a particular problem using the same concept. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.